All right. Also, for you former students, if you have some suggestions you want to make, go ahead for changes this semester. Try to accommodate whatever might be more helpful. But yeah, you can turn it in later. If you guys have it done, we'll collect them so you don't forget. Okay, thank you. Thank you. Okay, any more surveys? All right, let me tell you how I would approach HCl. You know, if somebody asks me, what are the chemical properties of HCl? I'll tell you how I wouldn't approach it first. If somebody asks me, what are the chemical properties of HCl? I wouldn't do this necessarily. You know, what are the combination reactions HCl undergoes? What are the decomposition, the acid base, the single replacement, double replacement, combustion, precipitation? Although that would be a good start, you know, if you didn't know what to do, etc. The way I would do it, if somebody asks me, what are the chemical properties of HCl? I would just say, you know, what are the metathesis properties? Now, the question is, what are metathesis reactions? Metathesis reactions are just, you know, when we look at HCl, HCl consists of the ions H plus, let's say, and Cl minus, or hydronium and Cl minus in solution. And so what ions does H plus like? Well, H plus is acid, right? And so basically it likes all bases, the anions are bases, so think. So there could be a lot of anions, although chloride's not one of them, you know. Chloride, otherwise, if H plus really liked chloride, it would bond together and stay stuck together, right? Well, the chloride's not a very good base. In fact, chloride's such a weak base, we call it neutral solution. And so it basically likes, you know, stronger things like hydroxide. Hydroxide's a pretty good base, etc. But those could be also classified as acid-base reactions, because hydroxide's a base, carbonate's a base, sulfide's a base, etc. Chloride.
Is cyanide one?
Yeah, cyanide. H plus loves cyanide. In fact, you're never supposed to never mix acid and cyanide-containing minerals. You know, if you mix acid with cyanide, you're going to get HCN. They say when you get HCN, you should smell burnt almonds before you pass away. Burnt almonds. What's that? So those are from survival stories. Yeah, yeah, lots. Sulfide too. H plus loves sulfide. H2S, rotten egg odor. You know, somebody in Ventura died recently from H2S exposure. Recently, meaning in the last 10, 15 years. Surprising that people still die from H2S exposure. Yeah. But what happens with H2S is it desensitizes your nose, so you don't know when you're being exposed to lethal amounts of it. Okay, so H plus, lots of things we can think of H plus reacting with, but what about chloride, you know? What ions does chloride react with? Silver ions? What else? Not sodium, because, you know, sodium and chloride, they don't really come together to form a precipitate. They break apart in solution. They'll come together when they're forced to. And they're forced to when you evaporate all the water. When you evaporate all the water, then the sodium and chlorides. And the interesting thing is sodium chloride has very high lattice energy, you know, 700 kilojoules per mole. Pretty high melting point. So it seems stable, but it's not as stable as something like silver chloride.
How about mercury 2 chloride, like HGE2?
Yeah.
CI.
Right. Mercury 2. Mercury 2 chloride, unfortunately, is not
No, I mean HG with the 200 substrate.
Oh, that's not mercury 2. That's,
Mercury 4?
no. This is called mercury 1.
Mercury
Hg2, 2 plus is mercury 1, or mercurous. Yeah, this reacts with. HgCl2 is soluble. Hg2Cl2 is insoluble. It forms a precipitate. Yeah. And one more. Not iron. Lead. And so, HCl will precipitate out with silver ion containing solutions, mercury 1 and lead 2. Then we look at acid base. Well, there's a ton of bases that we can pick that'll react with HCl. HCl is a strong acid. Then we look at redox. In terms of redox properties, H plus is what we call an oxidizer, chloride's a reducer. Chloride's not a very good reducer. H plus is a powerful or moderately powerful oxidizer. And so the redox properties, HCl, most people think of HCl as an oxidizer, right, because of the H plus. Mid-strength. Chloride, it could potentially react as a reducer. Okay, there are certain reactions that might not fit these categories, perfectly, like, photochemical reactions which form free radicals, that kind of stuff, but that's okay. For us, this is going to be the basics. Well, the reasoning behind the grouping is due to driving forces. And driving forces all have something in common. We're going from less stable to more stable. And so what makes something more stable? What makes something more stable is a strong precipitate, right? Strong precipitate's hard to dissolve, hard to melt, etc. But is that the same for every type of reaction? You could form a strong precipitate in a redox reaction and have nothing happen. Why? Because redox is a bit different. And so when we're looking at driving forces, we're looking at forming more thermodynamically stable products from less stable reactants. How do you describe those? Well, we'll look at it. How do you describe those? You describe them differently. For example, precipitate in metathesis reaction is very good, but a precipitate doesn't tell you anything in a redox reaction. A gas formed in a metathesis reaction is very good, but a gas formed in a redox, no big deal. So let me give you an example of this. And this is why we subcategories in this way. So I'm going to take, let's take this reaction here. I'll form a gas. And so if I take two H2O liquids, and I'm going to form 2 hydrogen gas and an oxygen gas, I'm going from 2 moles of liquid to 3 moles of gas. This is forming a lot of gas, right? 3 moles of gas. It's like 3 moles of gas under normal conditions is about how many liters of gas am I forming? How many liters of gas is that, roughly? 60, 67? Well, that might be a little low side. This is more closer to like room temperature, more closer to like 75 liters of gas. 75 liters of gas from 2 moles of liquid water. How much volume is 2 moles of liquid water? A mole of water weighs how much? 18 grams. A mole of water weighs 18 grams, which is how many milliliters? 18 milliliters. So we're going from 36 milliliters of water to 75 liters of gas. That's huge gas formation. So this must be a tremendous driving force, correct? No. So gas formation would have worked, in something like, the CO2 formation that we had earlier. But it doesn't work here. Why? Well, this is something we have to think about. There's no driving force for this here. In fact, the driving force is the reverse. Gas consumption. The reason is because redox reactions also share something else in common. You know, when somebody asks, you know, you don't want to exceed your daily sodium intake, are they talking about, what are they talking about? Are they talking about sodium ion or are they talking about sodium metal? They're talking about sodium ion because you wouldn't want to be eating sodium metal, right? Because that would cause you severe problems. You know, some people say, okay, you know, to help with radiation, you should consume some iodine to saturate your thyroid to make sure, you know, so they pass out iodine pills. Are they passing out I2, iodine, or are they passing out iodide? Do you think? Iodide. Interestingly enough, they have it figured out for both. So if you run out of iodide, you can still take iodine. Iodine is reactive, much more reactive than iodide. This is a different type of reaction. And so the thing about this is in redox reactions, we're looking at, what are the oxidation states? You guys remember oxidation states? Because if not, you got to go back to chapter 3 and get those down. What are the oxidation states in water? Yeah. And so -2 for oxygen, +1 for the hydrogen. What's hydrogen here? 0 and 0. So an oxygen with a -2 charge versus an oxygen with a 0 charge, are they going to react the same? Or are they totally different? Like a sodium with a +1 charge versus a sodium with a 0 charge, are they going to react the same or are they totally different? They're totally different. In Chem 4, they call this Dr. Jekyll and Mr. Hyde. In redox reactions, we're dealing with that a lot. And so what happens is this. When we have a redox reaction, we have to look at the stability of the charges. The stability of the charges on a particular atom dictate the driving force, not whether precipitate or gas forms. In metathesis are just ion combinations. The charges on the atoms never change. Even in the reaction that we just did, which was H2SO4 and calcium carbonate, let's look at the oxidation states here because we formed calcium sulfate, H2O liquid, and CO2 gas. So when we look at this is what we call a metathesis reaction or an acid-base reaction. You know, there are reactions that fit into 2 categories like this. When we look at the oxidation states, tell me the oxidation states in H2SO4. What goes first? Hydrogen +1. Then -2 for oxygen. That means sulfur is, these have to add up. -8 +2 +6. This is +6. Calcium carbonate, what goes first? +2 for calcium or -2. Usually the more electronegative, except for hydrogen. So -2 for oxygen. Carbon +4. Calcium sulfate, same, -2 +6 +2. Water, -2 +1. CO2, -2, and carbon is +4. Do we have any of this Dr. Jekyll and Mr. Hyde in metathesis or acid-base reactions? No, because if you look at it, sulfur stays as +6, carbon stays as +4. Everything, nothing's changed. It's charge, right? And so what do we look for? We look for other things that tell us stability. What are the other things? How stable is that precipitate? Gas formation, stronger to weaker acid. You know, we look for those things. But when we look at redox reactions, we're looking at Dr. Jekyll and Mr. Hyde. Now, when we're thinking about this, the energetics involved are usually quite a bit different. Do you have, you know, when you're doing a precipitation reaction, do you have to have an explosion shield usually?
No.
No, but if you do a redox reaction, it's probably a good idea to have an explosion shield. Like if you're taking hydrogen and oxygen gas, do you want to just do that in front of your face? Not really, because you're going to have an explosion, right? And so the energetics involved in this Dr. Jekyll and Mr. Hyde, the charges are quite big or can be potentially big. So redox reactions can be quite violent. compared to precipitation reactions or acid-base neutralization. When you're neutralizing a powerful acid like HCl with a powerful base like sodium hydroxide, do you have an explosion shield? No. I mean, it's a strong acid and a strong base, and yet no explosion shield. But if you take a strong oxidizer, like oxygen, and a strong reducer like hydrogen, you better have an explosion shield, right? And so energetics are quite different because of the charge. The charge, you know, when we think about the theory of chemistry, we're looking at the charges, right? Charge density. You guys remember electrostatic potential maps? That kind of stuff? We're always looking at the charge associated with that. And so metathesis and acid base, we're just looking at, you know, all the oxidation states stay the same. Metathesis and acid base, we're just looking at, you know, what constitutes stability. So in an acid-base reaction, a stronger acid is more reactive, less stable than a weaker acid. So we go from stronger acid to weaker acid, stronger base to weaker base. That's the driving force for acid-base. Metathesis, the driving force will be precipitation, you know, forming stable precipitate, gas formation, stronger acid to weaker acid. Same kind of thing. There's a lot of these are similar. But redox is totally different. What do we look for in redox? In redox, we look for stronger oxidizer to weaker oxidizer, stronger reducer to weaker reducer. We're going to go through these in detail, so we'll have to worry about that. And so when we look at for chemical reactivity, HCl has metathesis properties, acid-base properties, and redox properties that we look at. So these are our three basic types. Then we could subcategorize them. For example, in acid base, we have the Arrhenius, Bronsted, Lowry, and Lewis. For redox, we have single replacement, skeleton, redox chart method, etc. For metathesis, we have double replacement, ion combinations, etc., etc. You know, depending on how or what pattern you're looking at. So we could look at subcategories if you want. For acid base, we will, but for the others, not so much. And so when we're predicting reactions, we have to have some basic assumptions. Otherwise, you know, our predictions might come off. And what are the basic assumptions that we make when we do this? We want the solutions to be at standard concentration. Do you know what standard concentration is? The standard concentration, standard thermodynamic concentration. Is it 0.1 molar, 0.01 molar? Go back to chapter 7. What was the standard concentration, chapter 7? Do you guys remember thermodynamics, part 1? I would say review oxidation states for sure. Review some of the thermodynamic stuff also. Standard concentration is 1 molar. Gases, standard pressure, 1 atmosphere or 1 bar. Our book is 1 bar. Because our book is based Canadian University. U.S. it would be atmosphere, for sure. In Canada they use the metric system. All right, we call this, remember this? You guys got to remember this, delta H naught. What does this little superscript 0 mean? Standard thermodynamic conditions. What are standard thermodynamic conditions? This is a review again. Standard thermodynamic conditions are solutions of 1 molar and gases at 1 atm or 1 bar, and temperatures at room temp? No. David has it right. There's no standard temperature in thermodynamics, right? There's a common temperature. The common temperature is 298. And so when we're doing the standard enthalpy of formation, then we know the conditions, right? Or the standard enthalpy of whatever, standard enthalpy of reaction. And so we're going to just repeat this here. Extremely low or extremely high concentrations will obviously change things. You know, extremely high or extremely low concentrations are going to change the reactivity. Usually things become much more reactive at high concentrations. You know, when I was taking Chem 1B, we had a research project that everybody had to do. Everybody had to convert silver chloride into silver nitrate. Silver chloride's insoluble. How are you going to dissolve it? What are you going to dissolve it in, right? And so I was going through all these. You know, I tried silver chloride with nitric acid. No driving force. It's silver chloride with nitric acid. And so I was really stumped because the first step was, how am I going to get the silver ions freed up from the... And so what is silver chloride soluble in? It's not soluble in water. It's not... You think silver chloride is soluble in alcohol?
No.
No. Do you think silver chloride is soluble in hexane?
Yes.
Benzene?
No, benzene for sure.
Benzene for sure? Benzene's nonpolar, hexane's nonpolar. So is silver chloride nonpolar or very polar? It's very polar. Silver chloride is extremely polar because it consists of the positive silver ions and the negative chloride ions. There's huge polarity there. Polarity is when you have like a dipole, you have two separate charges, you know. So silver chloride is very polar. But if I knew obviously if I knew what I knew now, it wouldn't be maybe that difficult. So water is not polar enough to dissolve silver chloride. And so, the things you try, strong acid, strong base, etc. So, couldn't figure it out. Well, nothing gave me a driving force. Reason nothing gave me a driving force is because I was stuck. I was stuck at these standard assumptions. But, it turns out that silver chloride, well, here it is. This is the example from experience. Silver chloride and nitric acid, we get no reaction. Why? This is a double replacement or a metathesis reaction. What forms? Silver nitrate and hydrochloric acid. Nitrate salts are all soluble. Hydrochloric is aqueous. So we aren't forming precipitate. This is double replacement. We aren't forming gas. Are we going from a stronger acid to weaker acid? We're going from a weaker acid. Both of these are strong acids. But one of them is stronger than the other. Do you know which one's stronger, HCl or nitric?
HCl.
How do you know that?
It's a complicated process.
Well, most people, what they'll do is they'll just look it up. They look it up on an acid chart like this. HCl is a stronger acid than nitric acid, although this is hard to read. So we're going from a weaker to a stronger acid, but both of these are strong. And so you should know the leveling effect. Somebody remind me what the leveling effect is. What is the leveling effect? I don't talk about the leveling effect in these PowerPoints. I assume everybody knows it. What is the leveling effect? They're the same strength. In water, they're the same strength. Because if I had 1 mole of HNO3, what does it make? It makes 1 mole of H+. But 1 mole of HCl, it makes 1 mole of H. They both make the same amount of H+ in solution, so they're the same strength. They're both strong electrolytes, so they both dissociate 100%. So all strong acids, except for H2SO4, are the same strength in water. And so it's a tie. I wouldn't say this has no driving force because we're going from weaker to stronger. They're a tie. 1 molar HNO3 has the exact same amount of H+ as 1 molar HCl. Tied by loving. Now, weak acids make different amounts of H+. Well, it turns out you can dissolve it. You can dissolve silver chloride, but you use hot nitric acid. And the products are a little bit more complicated because there's some redox going on here. It's not just simple double replacement as I've shown it here. But anyway, let's look at some of these examples here. HCl and silver nitrate, this forms silver chloride, and HNO3, we get a precipitate. So double replacement reactions, driving forces of precipitate. But very dilute concentrations of HCl and silver nitrate will yield no reaction. You know, that's because you need a certain amount to get a precipitate. And if you don't have it, you could still have it there. You could be mixing HCl and silver nitrate and just get nothing because you don't have enough. It's too dilute.
Oh yeah, there's something called a KSP for a certain solid.
Right. Exactly. Which we're going to talk about much later. It's like the thing, you know. Would you pay me $10 to drink some HCl? You want to see me drink some HCl?
No.
You know, the reason I say this is because I just remember when I was taking high school chemistry, the chemistry teacher would always say, you know, you mix HCl and sodium hydroxide, you can drink it. But he never did drink it. It's just salt water.
Salt water.
So,
Did you drink it? It's not dangerous.
but the thing is, actually, you drink it all the time. You know, you drink it from the tap. You know what the pH of this tap water is?
6-ish?
5-ish. You know, it's the pH of this tap water is like 5. It's a lot of HCl's in there already. You're drinking it. So anyway, I wouldn't pay anybody to drink. Actually, I wouldn't pay anybody to do anything dangerous, of course. But anyway, we go back here. And so concentration is going to have a big impact. The same thing here. Lead-2 nitrate with sodium hydroxide. Under normal concentrations, we get a precipitated lead-2 hydroxide, but if you add high concentrations of sodium hydroxide, you're going to get no precipitate at all. We get this species. This species is a very strange species, and this is what we're going to start off talking about. Have you ever seen PbOH3 with a negative charge?
No.
This actually, and this changes a little bit due to another reaction that goes along, but this would be called trihydroxyplumbate ion, plumbate 2 ion. And this is called an example of complex ion, which we're going to talk about in chapter 24. So we'll learn about these and learn to name them. Well, the thermodynamic driving force is, okay, so concentration is going to have an impact. The other thing that's going to have an impact is kinetics. In order to properly predict whether a reaction is going to occur or not, we have to understand the thermodynamics, that is, going from less stable to more stable. But we also have to understand the thermodynamics. The thermodynamics is, you know, what path does it take, you know, to get to that stability. If it's an easy path, then the reaction should happen no problem. But if it's a difficult path, like this, graphite is more stable than diamond. But do you have to worry about your diamonds decomposing? No. Your diamonds are not going to decompose into graphite because of kinetics. In order for your diamonds to decompose, you have to break all those sp3 sigma bonds, right? And replace them with sp2, and pp pi bonds. It's not easy. And so kinetically, this is too difficult. And so we have a word for this. The word is metastable. Did I write that here? Yeah. Diamond is metastable. That is, you're not really going to worry about it reacting. Metastable means thermodynamically unstable, but kinetically stable. And so that could throw off our predictions, because if the kinetics are off, then nothing's going to happen. We're going to talk about kinetics later. Anyway, with all these exceptions, is it really worthwhile doing this? Because the reaction is going to depend on the distinct conditions. Yes, it's worth doing this because then we have a frame of reference, and then we can alter that frame of reference to compensate for high concentrations or whatever else. And so let's take a look at metathesis reactions first, and then we'll look at acid-base and then redox, or redox and then acid-base. I can't remember which one, but looking at metathesis, you know, we're looking at 2 or more ionic compounds or ions or whatever. And what the goal is to find favorable ion combinations. You know, what ions like each other. You can figure out what ions like each other because the ions that like each other tend to form precipitates, or tend to form gases, or weaker acids from stronger ones.
Wait, the ions that like each other tend to form acids?
Yeah.
So is hydrogen chloride in that list? So that means they like each other?
Well, hydrogen chloride, if they're in the aqueous phase, some of it. This is what we call you know, partial reaction. Most of the hydrogen chloride in water will like to associate with other water with water molecules, And so we call those hydrated or solvated ions. So chlorides are going to be surrounded by waters. Hydronium or hydrogen ions are going to be surrounded by waters, right? Hydrogen ions are going to react because they're too reactive, but some of those can combine together to form HCl gas. So this is why you never leave the lid off the HCl. If you leave the lid off HCl, what's going to happen? Eventually it's going to go flat, right? So you might start off with 6 molar, but somebody leaves the cap off for a week. Is it still going to be 6 molar? No, because some of the HCl will have been evaporated off. You know, it's not strong. You know, let's say if H plus and Cl minus really liked each other, you leave the cap off and then 1 hour later it's gone, right? It's flat. It's like soda. You know, if you have soda water, 1 hour later, is it still fully carbonated? No, but if you have 6 molar HCl, it's still pretty close to 6 molar 1 hour later. You know? And so this is the difference in driving force. The same thing with ammonia, you know, and water. And so gas formers are like this. You know, if you have, let's see, if you have, let's say, sodium sulfide solid, and you add some HCl to this, AQ. So HCl added on top of this solid sodium sulfide, then the H plus and the sulfide really like each other. And it's going to form H2S gas, bubble up. This is why you never add acids to sulfides, because H plus and sulfide really like each other. Sulfide's what, you know what sulfide is? Sulfide's a base. How strong of a base is it? Would you say weak, moderate, or strong?
Moderate.
Sulfide's a strong base, right? In fact, sulfide is stronger than hydroxide. And so obviously H plus is going to love sulfide, right? Being a more powerful base than hydroxide. Well, anyway, we go on here. We look at weak electrolyte molecular compounds might participate. And so usually in metathesis we look at ions. However, there's a class of molecular compounds that participate, and these would be the amines. You know, organic compounds are classified depending on their structural group. And amines are all going to have this nitrogen bonded to either hydrogen or carbon. Hydrogen and carbon have comparable electronegativities. Since hydrogen and carbon, hydrogen is a 2.1, carbon's a 2.5 on the Pauling scale. It doesn't change the electronic, you know, charge density on nitrogen much. And so all these amines are weak organic bases or weak bases. Have you dealt with amines? Chem 1A? Did you talk about the amines? We talked about amines briefly. 1A. Anyway, the amines are ammonia-like compounds. They behave like ammonia. What happens is ammonia and water, ammonia is a weak base. What do weak bases do? Weak bases partially ionize, or weak bases partially hydrolyze? What is more correct, ionize or hydrolyze? A weak base is partially hydrolyze. Hydrolyze means it reacts with water and breaks water apart. And so weak bases like ammonia hydrolyze. So ammonia and water form what? Ammonia and water form ammonium and hydroxide. Small amounts. That ammonium ions and hydroxide ions, well, those can participate in metathesis because those are ions. And so for weak electrolyte, that is these weak bases, the amines we call them. Amines, the spelling's important here. The amines are spelled with one M. And so we call this the amines. Amines. Examples of amines would be something like this: CH2, CH3. This would be called. Oops, NH2. Sorry, not NH2, CH3. You know what CH3 is called in organic chemistry? Somebody remind me. CH3 group is called what? Methyl. This is called methylamine. Right? Ethylamine, propylamine, dimethylamine, trimethylamine. Trimethylamine, those are all bases. They're all going to hydrolyze water the same way. It's just that rather than having a hydrogen, you have a methyl group or whatever. But because of the similar electronic properties of carbon and hydrogen, it doesn't change the acidity much. Versus if you have something like this, is this an amine? NF3. Is this going to behave like ammonia? Well, it's got a lone pair. So will it behave like ammonia?
No.
Ammonia has a lone pair. Amines have a lone pair. Why doesn't this behave like an amine? Because all of a sudden, now we're going from an electronegativity of 2.1, 2.5 to electronegativity of 4.0. In fact, it's going to change this totally. You can see this. People who are, do you see this right off? Look at the oxidation states. Totally flipped. What is this oxidation state here? Fluorine goes first at -1. Nitrogen is... What are the oxidation states here? Have you done oxidation states based on structure? Can you tell me the oxidation states in methylamine? Carbons +4. Carbons +4? -4? No.
No.
No, carbon's not -4. Actually, I don't have time to do this. We need to do oxidation states based on structure because some of the more complicated structures, when you do oxidation states based on a formula, what you get is the average oxidation state. You don't get the individual oxidation state. So for example, let's look at this compound, which you might have seen in Chem 1A. Fe3O4. This one is important for geologists. You know how geologists find Fe3O4? Fe2O3 is red rust. Fe3O4 is different. Do you know how geologists might find some Fe3O4? They use magnets to find it because this is called magnetite. Right? This is the mineral magnetite. What are the oxidation states here? Okay, -2 for the oxygen and iron. Well, this is -8.
It's one of those fractions.
Yeah, this is going to be plus
8 thirds.
8 thirds? Plus 8 thirds? Okay. Plus 8 thirds. That means I have 3 irons. Each iron is plus 8 thirds. Is that what that means? No. It means that I have 3 irons and the average oxidation state on the iron is 8 thirds. What are the oxidation states? Yeah. And so we know the oxygens are going to be -2. We got 4 of those. And so we got to figure out, this gives us -8. We got 3 irons. And this has got to give us +8. -8 plus 8 is going to give us a neutral compound. And so it's 8 thirds, but in reality it's +3, +3, and +2. We got 2 +3 irons and 1 +2 iron. So, it makes a difference. We don't want the averages often. We want the individual rather than the average. And so this is why I bring up this. In this case, probably doesn't make any difference. We'll probably still figure it out. But for molecular compounds, for ionic compounds is a bit easier. But for molecular compounds, the way we do it is this. It's, somebody tell me, when we come up with oxidation states, we're assuming that the bonds are 100% covalent or assuming the bonds are 100% ionic? When we do oxidation states, we make an assumption. Did you know that?
No.
What assumption do we make when we come up with oxidation states? This is the charge on that atom if we assume what? It's 100% ionic. Do you know formal charge? Formal charge, we make the opposite assumption. For formal charges, this is the charge on the atom if we assume 100% covalent. Right? And so actually assigning structures is easy because it's winner take all. Who's more electronegative, carbon or hydrogen? Carbon or hydrogen? Carbon. Carbon's 2.5, hydrogen's 2.1. Carbon's more electronegative. Winner takes all. Oops. Winner take all, winner take all. Carbon versus nitrogen. Nitrogen. And so carbon ends up with a total of 2, 4, 6 electrons. It's supposed to have 4. There's 2 extra electrons. 2 extra electrons are going to give it a negative charge or a positive charge? Negative charge. The oxidation state on carbon is -2. Not -4. Hydrogens, well, these hydrogens end up with nothing, so it's +1, +1, +1. Okay, this nitrogen. Ends up with what? Ends up with 2, 4, 6, 8. You know, nitrogen versus hydrogen. Nitrogen can take all. Winner takes all. It gets 8 electrons, normally has 5 electrons. It ends up with -3 because it has 3 extra electrons. This is -3. The hydrogens end up with +1. In Chem 1A, I call this compound electron rich or electron poor. Electron rich. Electron rich compounds burn. They combust. So methylamine should be combustible. But you don't want to combust it because in combustion or redox reactions, and sometimes the products can be toxic, like oxides of nitrogen or other things. So you have to be careful depending on how completely you combust it. If it's completely combusted, it'll probably form nitrogen dioxide, CO2, and water. Yeah. Completely combusted with O2. But anyway, those are some of the properties you can get. We can get other properties. Primarily, you know, when we look at oxidation states, we're looking at redox properties. But in this case, we're looking at acid-base. Do you see these 2 nitrogens are totally different? This one we call amines. All amines are going to have a -3 oxidation state in the nitrogen when you look at the pattern. This one is not a base at all. This one would be much more acidic.
What?
You don't have to worry about that. We'll talk about acid-base. This is called Lewis acid-base. Lewis acid-base is much more complicated because we look at it atom by atom. You know, what's the active site, or what's the atom that's going to be most acidic? What's the atom that's going to be most basic in the structure itself? Some are what we call amphiteric. There's acid sites and base sites within the same. And so it could react either way, you know. So amines like this, you know, this is going to be a base, a weak base. This is going to react with water to form what we call methyl ammonium ion and hydroxide. The hydroxide, you know, a lot of metal cations precipitate out with hydroxide. So when you add ammonia to a aqueous solution containing metal cations that are insoluble hydroxides, you're going to get a hydroxide precipitate, usually. Not always, we'll see later. So when we're looking at metathesis reactions, the first driving force we look for is precipitate. And so for precipitates, you just remember your solubility rules. The solubility rules for ionic compounds, I'd like to go off the one in the lab manual, not the one in the textbook, because the one in the textbook is a little more difficult to memorize. You know, the one in the lab manual is a little easier to memorize. And there's always exceptions, you know. These are just, would you call this a law? You know, this is the law of insoluble solids or law of precipitates. Would you call it a law? You know, when we're doing the scientific method, you know, what do scientists do? Usually what scientists do is they take down observations. And so what are the observations we're going to take down here? Observations that we're going to take down are that, in general, group 1 and ammonium compounds are all soluble. There are some exceptions, you know. For example, sodium can actually precipitate with something called uranol and acetate. The uranol ion and the acetate ion form sodium uranol acetate, which is an insoluble sodium compound. But, you know, those are more rare, right? And so group 1 and ammonium compounds are all soluble. These are patterns that we see or observations that we get. 2. What's 2? You guys have these memorized still or not? Did anyone not have to memorize the solubility rules? Okay. Yeah, the easiest way to memorize these is just keep writing them over and over again. Okay. 2. Nitrates, acetates, and chlorates are all soluble. Is that right? Yeah, and then we go to chlorides, bromides, and the iodides are all soluble except for silver, lead, actually silver, lead, mercury. Right. Sulfates are all soluble except for silver, lead, mercury, calcium, strontium, barium, etc. And so we get that. Now, those are just our observations. So we group them into patterns. You know, this is the patterns that we observe, so we don't have to memorize every single thing. You know, and from, you know, these patterns or trends, you know, it could be trends as well. Sometimes we can come up with laws, you know, if those patterns or trends consistently hold. This one we wouldn't call a law because there are too many exceptions, right? We would like things with less exceptions, call it a law. But do you know where laws can lead to? Yeah, laws can lead to, usually hypothesis is your first attempt at a theory, and then ultimately we want theory. You know, and so what we try to do is we try to look at the solubility rules. You know, and some patterns that people see, you know, for example, the higher the charge, the less soluble or the more soluble?
Less.
The less soluble. The higher the charge, the less soluble. Why?
Take for example.
Yeah.
Take for example, iron 3 hydroxide. It's insoluble compared to calcium hydroxide, which is a 2+ charge.
Yeah, that's good. Yeah, higher the charge, the stronger the ionic bond, the more difficult it is to break, right? But then you go, well, what about silver? Silver is only +1. Chloride is only -1. Why does silver chloride precipitate, but sodium chloride does not? And then you go, wow, that just failed. But it really didn't fail because, you know, we got to look at bonding. You know, when we look at bonding is a little bit more complex than just looking at charges. You know, do you guys remember bonding theories? What 2 bonding theories did you learn in Chem 1A? Valence bond and molecular orbital. And so we're going to be looking at that in more detail too, to help us understand these things. Because when we do that, then the silver chloride exception is much more understandable. All right, let's take another break. Actually, we're going to go till 12:35. Is that correct?
Yeah.
So let's take a 10-minute break and then have the last part of this happens.
Yes.